Alright, so we align the transmitter with the receiver and we start the pulsing so we can do the modulation, so we can find background subtraction from the signal plus the background. And we use a retroreflector up there to co-align so that the person on the transmitter can see when they're pointed accurately. And we
significantly reduces alignment time.
Yeah, and we're using an oscilloscope temporarily for seeing the signals on each of the channels. And as you can see, probably want a video of that. 1 second pulse with scintillation, the red being the smaller of the two apertures. Okay.
And that goes from there.
Can you see the red laser?
Oh yeah, you can see the laser in the background.
Okay, so anyway, I just told this to take 60 sessions of data, which is about an hour worth of data. We'll stop it prematurely whenever we want to, but we're going to see how this is working. This is with a lot of changes. We got rid of voltage offsets, so we were able to level out our amplifiers, and we changed both detectors to be the same size detector, and we apertured one down so that we had our 1 millimeter diameter, even though we were using a bigger detector. This will allow us to have the same background noise and the same rise and fall times, so we don't have to worry about any differences in the circuitry. So the only difference will be aperture size. All right, let's go ahead and run this and see what happens. All right, it's collecting data now. So we're collecting 600,000 samples, 300,000 per each aperture for 30 seconds, which is 10,000 samples per second. We're actually running a little slower than that. We're running more around 8,200. So we have a little headroom. We've got a couple seconds of extra data, and we use that so that we can align everything, all the data, and get rid of some of the beginning and some of the end, and we have a perfect set where you start with the on periods versus the off periods, and that's how we parse the data at the end. And so we end up with like 114,000 samples of on period versus 114,000 samples of off period. That's with removing junk, so the first few snippets of the on and off periods, and with removing the pre and post of the whole signal. So you end up with total comparison of like 228,000 samples. Okay, the first reading shows CN squared is not a very good. It's not a very good prediction actually. It's saying 1.2 millimeters for the inner scale, and it's saying CN squared is not the same on each aperture. So I don't know why the other method works better. It doesn't make sense. That is really weird.
We're still aperture averaging, right?
We are.
So it should still just come out, right?
That's what's really weird about the situation. It's not the. I don't think that using the two same detectors and aperturing one down is the problem. I think it's because I'm removing that offset. It's almost like that offset has to be there to keep the calculations correct. When we do the math, we must be overlooking something, because the math says that we should be able to remove the DC offset, but when I do that, the numbers don't come out right. If you notice here, the background subtraction and the pre and post background subtraction, they're identical, which means there was no background to subtract because I did it electronically.
Yeah, we saw that in the data too, right?
Yeah, I got rid of it electronically, but when I just leave it all in there, we get the numbers that make the most sense. So something's very, very weird.
Are we gonna pause it and remove the background
Yeah.
algorithm?
Mm-hmm.
All right.